All right, so finally we're going to talk about the last piece of the UV vis instrument, and that's the detector. And the detector does a specific job, and that is to see the data. And the detector is what picks up the light difference, the light coming in to the light coming out, and it's what gives you the absorbance or the percent transmittance on the UV vis instrument. All right. So the detector is made a certain way, and quite honestly, the detectors in spectroscopy are all very similar. Once you learn how the detector works in this machine, that's typically the detector that's used in every one of them, at least for the majority of the pieces that we'll talk about this semester. All right. So the detector in this case is called a PMT. And the PMT is not CMT, country music television, but the P stands for photo, and the M stands for multiplier, and the T stands for tube. So photo multiplier tube, PMT. And the photo multiplier tube is basically the way that it takes a signal from the machine, amplifies it, and gives it to a software system like a computer. Okay, so the way that this thing works is that light source comes into the PMT tube. Now, this is the detector, and I'm just going to draw a big box here. And then on this box, there's going to be kind of like a screen, and I'm going to draw little balls on them. All right. So what happens for the detector is that the light source comes in, and the light source hits the basically plate that has electrons on them. Okay, so these are all electron driven. And it knocks a few of the electrons off. Okay, and then there's going to be other plates in the photomultiplier tube that's loaded down with electrons as well. So it's going to hit that plate, and it's going to knock more electrons off, and that one hits that plate and it knocks more electrons off. And then there's going to be another plate with more electrons, and then that one hits and knocks more off. This one now hits, knocks more off. This one hits, knocks more off. This one hits, knocks more off. And this will keep going and going and going and going and going. And then by the time that you're done, you have amplified the signal because it's electron driven. That's why we call it multiplier tube. Okay? So we're starting off with a very weak signal, and due to the domino effect of us dislodging these electrons off of these plates, we're gathering more and more electrons as we go through. And that's going to create a current or a signal for us that our detector can pick up, amplify, and then send it to the software system. Okay? These detectors, the PMT tubes, they are not cheap. The PMT tubes are anywhere between $2,500 to $3,500 if we're using them in the old school instrumentation. We've actually not had to purchase one for a new UV Vis, so I would hate to see what those would cost. But we've had to replace them for the old ones, and this is how much these detectors are running. So the detector is quite a bit of money. And when you're talking about a machine that's $9,000 or $10,000, and that one detector is anywhere from $2,500 to $3,500 of that money, then this can be expensive and it can get outrageous. So that is what we call the detector. It is a PMT, photomultiplier tube, and it gets a signal from a very weak delivery, and it amplifies that, and it makes it bigger and bigger and bigger until it comes out the other end with a full-blown signal. It kind of exaggerates the signal is what it does. I mean, that's its purpose. All right? Okay, so let's take a look now of the overall scheme of things now that we've taken a look at all of the pieces and parts. So number one, we have a light source, and we've talked about the light source now, and that light source will shine through the sample. It could be a deuterium lamp, it could be the tungsten lamp, it could be the xenon arc lamp, but light goes onto the machine or onto the sample. Before it gets to the sample, a monochromator will separate the light into the individual beams, and then it goes into the sample and allows it to absorb. The detector detects how much light the sample has absorbed. So that detector again uses a photomultiplier tube, and it looks at these very weak signals and it amplifies them and it converts it over to the software so the computer can read it. All right. What I see on the screen is what we call a spectrum. So on my screen itself, I will see maybe a couple of humps depending on what type of compound I'm using. And this is what we call the spectrum. So I can take the spectrum of a molecule, and that allows me to find the tallest peak, and that tallest peak is what we call the lambda max. And it's that lambda max that I will run and analyze all of my samples and standards with because that's the most sensitive area, and that's the area that it's tuned to absorb the most light in. Okay? So that's the sequence of a spectrometer. Now, there's a couple of problems that we might have. One, when we go through and we start running samples, we might not get an absorbance of 0.1 to 1.5. And if I'm outside of this working range, things do not work for me. And that's because Beers's law does not work very well outside of that range. Lower than zero point 0.1 is typically an area where the samples are so weak it can't tell if it's absorbing or not. And then higher than 1.5 is the samples are too concentrated. So again, it can't tell the difference between a super concentrated and how it absorbs to a super concentrated and how it absorbs. There's just no difference, and it can't see them at all through them. Think about it as you looking through the cuvette. If something is too concentrated, it will be too dark. So if I put things that are too dark to each other, and one slightly darker than the other one, but to your eyes, you still can't see through it, well, the machine can't either. There's no difference there. Finally, some other problems that we might see in the UV and how to fix them. One is the solvent. Okay, solvents can cause us a problem because solvents can absorb UV light or visible light. So if I'm using a solvent, I have to make sure that I blank the solvent out of the machine so I can take that absorbance away from the sample. All right. If I make it with DI water, I blank it with DI water. If I make it in acetone, I blank out acetone. If I make it in methanol, I blank out methanol. That's why we do that. That solvent will typically cause me a problem if I don't correct for it. Not only that, I want to pick the proper solvent because if I put a proper solvent in, it will not react with the component that I'm trying to measure. If I'm using the wrong solvent, that solvent and the component can react together and it can give me a brand new substance. And I don't want that to happen either. So I want to pick something that doesn't react with each other or have a little side reaction in the cuvette when I go to measure. Another problem that I might see is the pH. The pH, depending on some indicators and some compounds, if it's too acidic or if it's too basic, the pH can make a molecule change. And think about phenolphthalein for a minute. Phenolphthalein is a common indicator that you've used in a laboratory. It goes from colorless to pink, and it only goes to pink in a basic solution. So could you imagine running phenolphthalein in the visible region with acidic conditions? It will be clear. I'll see no absorbance really at all. But if I'm not careful and I put a solvent in that changes phenolphthalein to a basic solution, then all of a sudden it goes bright fuchsia pink. Well, I'm going to get a different readout on the UV vis because of that. So I have to make sure that when I run compounds on the UV, that my pH is staying pretty much consistent from point A to point B, right? I don't want these things to change on me because that can give me different results according to the detector. Next is stray light. That can also be a problem. Stray light will typically come from the outside environment in. That's why you always run the UV vis with the lid closed. I can't tell you how important that is. always run the UV vis with the lid closed because visible light and UV light are present in the room. And that can get into the machine and that can start disturbing the detector and how things absorb. And they'll give you a faulty reading because of that. Next is not positioning the cuvette properly. So if I put the cuvette in there crooked, then I'll get a weird absorbance reading. If I put the cuvette in there and the cloudy sides are actually lining up with the light beam, then I'm going to get a faulty absorbance read. It will be about half of what it should be. So make sure that you're putting the cuvette in there in the right location in the right spot. Next, dust can also be a problem. Dust can scatter into the machine. So if I'm leaving the door open or if I'm using the UV vis often, a lot of times if the room's dirty, dust can settle down into that chamber and small little particles of dust can float around in that compartment cell. If that happens, it's going to do weird things with your absorbance beams, and you might get faulty readings because of that as well. So always make sure that your UV vis is clean. Make sure that there's no dirt or grime in the compartment cells. If so, you just want to make sure that you clean it out really well. Finally, fingerprints on the cuvette. That's typically the biggest problem that we always see. People forget to wipe their fingerprints or their smudges off. And when you do that and you forget that, all of these fingerprints will smear and the light beam will hit the cuvette and it bounces off and it bounces in different directions and it won't go actually through your sample. So you get a weird absorbance reading because of that as well. So you want to wipe all of the cuvettes clean before you place them in the spectrometer with a chem wipe, and always just kind of make that as a habit, like putting your seatbelt on, hopefully, when you get into the car. You shouldn't have to think about that kind of stuff. It should just come naturally for you. All right. So that's what we need to say about the machine and as far as the setup goes. So the light source, the sample compartment, the monochromator, the detector and how it talks to the CPU unit, and some troubleshooting problems that will typically happen if I'm not careful in the UV vis world. Okay? So in the next upcoming videos, what you will see is a couple of videos concerning the software of the thermogenesis that we have in our laboratory, and then a couple of videos talking about how to process a calibration curve and how to do some data analysis with the data that I get. So we're not finished with the UV cluster yet, but we're getting closer and closer there. So a handful of videos are left. You're almost done, and then you can go party and celebrate this weekend.